In this lecture, we show how one can set up a triple integral as an expression for the volume of a solid bounded by given surfaces. The solid is the region bounded by the surfaces 4x squared plus y squared equals 4 and y squared plus z squared equals 9. It also lies above the xy plane with x greater than or equal to 0. For this exercise, we write the volume triple integral using two different orders of integration that correspond to the volume element dv equals dz dy dx and to the volume element dv equals dz dx dy. The first volume element dz dy dx says that we integrate with respect to z first, then with respect to y, and finally with respect to x. For the second volume element, dz dx dy, we switch the order of integration for y and x. We will see how this switch in the order of integration changes the volume triple integral. Provided that we set up both triple integrals correctly, both triple integrals should evaluate to the same numeric value. On an added note, there should be 6 orders of integration corresponding to the different permutations of dx, dy, and dz. To see what the solid looks like, let us sketch the bounding surfaces, starting with the surface 4x squared plus y squared equals 4. On the xy plane, the graph of this equation is an ellipse, as shown on the image on the right. As an easy elementary exercise for the viewer can check that this ellipse has a major axis of 2 along the y-axis and a minor axis of 1 along the x-axis. However, this is an equation in the three-dimensional space R3, so what we should have is a surface. With the variable z missing, the equation corresponds to what we call a mathematical cylinder. Now, this is not the usual cylinder like a tube or a soda can that we might typically refer to as a cylinder. This mathematical cylinder is generated by the ellipse on the xy plane, which is a level curve for the surface. It corresponds to the z value 0. To generate the surface, we translate this ellipse in a motion parallel to the z-axis, and we get the image of the surface. The graph of the second surface, y squared plus z squared equals 9, is quite similar. This time, we examine the equation on the yz plane. The curve corresponding to the equation y squared plus z squared equals 9 on the yz plane is a circle of radius 3. Since the variable x is missing from the equation, we generate the surface by translating the circle in a motion parallel to the z-axis. We take only the front half because x is supposed to be greater than or equal to 0. And we take only the upper half since the solid is supposed to lie above the xy plane. So the solid is the portion inside half of the first cylinder which had elliptical level curves, and the upper half of the second cylinder, which had circular cross-sections. This red curve is the intersection between the two cylinders above the xy plane. Let us take out the extra bits protruding from the solid. So here is what the solid looks like. To set up the volume triple integral with the first volume element dv equals dz dy dx, we need to write down the different inequalities for the different variables. This should help us with the setup of the volume triple integrals. First, the inequalities for z, the first variable of integration. The key is to follow the direction of the z-axis. dz, z-axis, that should be simple enough. We check the lower surface boundary and the upper surface boundary. The key phrase here is surface boundary. The lower surface boundary is on the xy plane where z is equal to 0. The upper surface boundary is the surface whose equation is y squared plus z squared equals 9. On each of the upper and lower surface boundaries, we need to solve for z in terms of x and y. Note, and this is important, the first variable of integration is z. We have to solve for z in terms of the other remaining variables, which are x and y. On the lower boundary, which is on the xy plane, z is simply 0, so there's nothing to do there. On the upper boundary, where y squared plus z squared equals 9, we solve for z to get z equals plus or minus the square root of 9 minus y squared. And because the solid is above the xy plane, so that z is greater than or equal to 0, we take the positive square root, so that z equals the square root of 9 minus y squared on the surface. There is no x variable here. That's okay, as long as we're able to solve for z. The important thing is to ask if we follow the z direction anywhere on the solid, on which surface do we start, and on which surface do we end? And is it always this same pair of surfaces all throughout the solid? The answer to this last question is a resounding yes. We always start at z equals 0 at the bottom and all the way without interruption to the top where z equals the square root of 9 minus y squared. This is important because this means we need only one set of inequalities for z in the region. So we have 0 is less than or equal to z less than or equal to the square root of 9 minus y squared. So we are done with z. This means the variable z should not make a reappearance in the subsequent inequalities that we generate. Now for the second variable of integration, which is the variable y. We look and see what is called the projection of the solid on the xy plane. Well, x and y are the remaining variables, hence look at the xy plane. That should be simple enough. But exactly what is the projection of the solid on the xy plane? Imagine for a moment that we leave a heavy object like the solid sitting for a few days on the same spot on a carpeted floor. The carpeted floor here would be the xy plane. Then after a few days, we lift the object and move it elsewhere. Now we would expect that there would be a depression or impression that the object would have left on the floor. This depression is what we call the projection on the xy plane. We need to find the equation of the bounding curve of the projection. Since the projection is on the xy plane where z equals 0, we set z equals 0 in the original equation for the surface containing this curve. Now remember that this red curve is the ellipse which is part of the surface 4x squared plus y squared equals 4. There is no z, and since the original equation has no z variable to begin with, we just take the equation as is. 4x squared plus y squared equals 4 is the equation of the ellipse. Now, that was easy. Remember now that the variable of integration is y. So we follow the y direction on this projection and determine this time the curve boundaries, not the surface boundaries, but the curve boundaries for this projection. The variable of integration again is y. So we solve for y in terms of the remaining variable, x. Now remember, we had already dealt with z. We should never have to deal with the variable z again. Solving for y in 4x squared plus y squared equals 4, we get y equals plus or minus the square root of 4 minus 4x squared, or plus or minus 2 times the square root of 1 minus x squared. For this elliptical curve boundary, there are two halves. Y equals minus 2 times the square root of 1 minus x squared, which is this lower half. The other half is y equals 2 times the square root of 1 minus x squared. We start from the bottom. From the lower quarter ellipse, y equals minus 2 times the square root of 1 minus x squared, and upwards to the upper quarter ellipse, y equals 2 times the square root of 1 minus x squared. The important thing is that there is no change in the pair of curves that we use for the projection. The question we ask is, do we always hit the same two curves anywhere in this projection? The answer is yes. So we have only one set of inequalities for y. We have minus 2 times the square root of 1 minus x squared is less than or equal to y, which is less than or equal to 2 times the square root of 1 minus x squared. Now that we have finished writing up the inequalities for y, like z, y should never make a reappearance in the subsequent inequalities that we have to write. And there is only one set of inequalities left, the inequalities for the variable x. This time, we are looking for actual values of x. The questions we ask are, what is the smallest value of x? And what is the largest value of x in the projection? For the smallest value of x, how far left can we go? Well, what do you think? The projection starts on the y-axis, so x equals 0 is the smallest x value. And where do you think the biggest value of x occurs? Well, it's right here, at the right x-intercept of the ellipse. Here, y equals 0, so that the equation of the ellipse becomes 4x squared equals 4. And solving for x, we get x equals plus or minus 1. Since x is greater than or equal to 0 for the solid and for this curve, x equals 1 at the right x-intercept. Therefore, we have 0, the smallest value of x, is less than or equal to x, which in turn is less than or equal to 1. We can now write the volume triple integral quite easily. Starting with the outer integral for x, which is the last variable of integration, we have the lower limit 0 and the upper limit 1. Next, for the variable y, we have the lower limit minus 2 times the square root of 1 minus x squared, and the upper limit 2 times the square root of 1 minus x squared. Finally, the innermost integral, which is for the variable z. The lower limit is 0, and the upper limit is the square root of 9 minus y squared. Because this is just a volume integral, what goes inside the triple integral is simply the volume element dz, dy, dx. Now let us tackle the volume integral with the volume element dv equal to dz dx dy. Here the order of integration for x and y are switched. Switching the order of integration does not necessarily translate into switching the corresponding integrals and sticking with the same limits of integration. That is frequently the wrong way to do it. We proceed as we did with the original dv, that is, by examining the different inequalities for the different variables. The first variable of integration is still z, so that the first set of inequalities stays the same. After all, the upper surface and the lower surface boundaries have not changed. The region still starts on the xy plane at z equals 0, and ends on the surface y squared plus z squared equals 9, where we had taken z to be equal to the square root of 9 minus y squared. For the remaining variables x and y, we still look at the projection on the xy plane. Recall that the projection is this half-elliptical region. This time, the second variable of integration is x. And because the next variable of integration is x, we follow the x direction on this projection to determine where x starts and where x finishes. Within the projection, we start on the y-axis, where x equals 0, and finish on the ellipse, where 4x squared plus y squared equals 4. Because x is the variable of integration, we solve for x in terms of y. Solving for x, we get x equals plus or minus the square root of 1 minus y squared over 4. Since x is non-negative for the solid, we take x to be the positive square root of 1 minus y squared over 4 for the half-ellipse boundary of the projection. And so we have the inequalities for x. For the remaining variable of integration, which is the variable y, We look for the smallest and biggest values of y within the elliptical region. The smallest value of y is at the lower intercept for the ellipse, and the biggest value is at the upper y-intercept. Solving for these intercepts, where x equals 0, we get y squared equals 4, or y equals plus or minus 2. And so we have minus 2 is less than or equal to y, less than or equal to 2. Now let's write the triple integral for the volume. Starting with the outermost integral, which is for the last variable of integration, the variable y, we have minus 2 for the lower limit and 2 for the upper limit. For the second variable of integration, which is the variable x, we have 0 for the lower limit and the square root of 1 minus y squared over 4 for the upper limit. And finally, for the first variable of integration, the variable z, we have 0 for the lower limit and the square root of 9 minus y squared for the upper limit.